Welcome back. In the previous video, I showed you one of the synthesis routes where you can go from a secondary alcohol to a ketone. That's one of the most popular methods because people just somehow remember primary alcohol when oxidized gives you an aldehyde and secondary alcohol when oxidized gives you a ketone. It's classic, so something you can expect on a test or a quiz or a homework. Now, this is something I have explained as part of when I was explaining the mechanisms for, um, when we were talking about the various aromatic electrophilic substitution. This was one of them, okay, which is Friedel-Crafts acylation. Now, acyl always produces a ketone, okay? That is, this is not alkylation, this is acylation. Okay, and the only product you can expect from a Friedel-Crafts acylation is a ketone. Now, remember, we generate an electrophile. The electrophile then reacts with the benzene and produces the final product, right? Now, I know some of you still struggle with this. So instead of you writing it this way, if you're comfortable, hey, by all means, do it this way. If you're still having trouble recognizing the number of carbons, write it this way. So this is CH3, C, double bond O, Cl. I think this will make a life a lot easier if you, so let me actually write the Cl a little bit. Okay, that's good. All right, now this reacts with the AlCl3, so, and this is not new, this information, I won't go into too much detail on the mechanism. I do, however, show part of the mechanism so you can still understand where we get the electrophile from. So this is one of the reactants that reacts with the AlCl3, and we know that this reacts with the Al, and in the process, we generate CH3, C double bond O, and because the bond is lost, the C gets the positive charge, plus AlCl4 minus, right? This then reacts with the benzene. Again, like I said, I don't want to go into the resonance structures of the benzene because I have explained in great detail Friedel-Crafts acylation when we talked about it. So I'm just going to, from here, not do the whole mechanism, but instead give you the final product. So this will give you the final product, which is essentially, if you think about it, I have just taken this portion, which is this, right? I have just taken this portion and added it to the benzene through this bond, right? That's essentially what Friedel-Crafts alkylation or acylation is. You won't have the C double bond O in the alkylation. You do have the C double bond O in the acylation. So this is a ketone, right? Remember, this is your R prime. This is whole thing is your R, and your carbonyl group is right in the middle. So it qualifies for a ketone. So this is Friedel-Crafts acylation, and this is one of the popular methods for making ketones. Now you remember this one? This is from Chem 330. This was in fact on the final. I'm not sure about the exact reactant, but this certainly was there. Ozonolysis, right? And that's because we are using ozone as one of the reactants, right? Now, whenever you add ozone to a compound containing a double bond, I'm going to draw this in a different color and then write the product in a different color so you can see what's happened. So this is your reactant. When it reacts with ozone, basically it forms this intermediate. If you remember it, this is something we did. Basically, you add the 3 oxygen in this style to your long chain carbon compound containing the double bond, and this breaks like this. Remember this? We did this for sure, yeah. So let me get a different color again. Okay. So what happens here is essentially you add a double bond O. I'm going to point out this is the carbon we're looking at, right? Containing the double bond, right? This is the carbon containing the double bond, right? Basically, you're adding a double bond O to this carbon plus a double bond O to this carbon. I don't want to go too far into the mechanism because I want to keep the video time to a minimum. So let me actually, does that make sense? Okay. So what we have done here is we've added a double bond O right here to this carbon and to this carbon. So this is a ketone. You remember, this is a metal, this is a metal. We cannot have hydrogens anywhere near this because if this were to be a hydrogen, then it becomes an aldehyde. So it has to be a metal. So if you're going to do Hall's analysis, the carbon containing the double bond must have a certain arrangement of groups around it for it to result in a ketone. Now let's say if I give you this, okay, let me step back. Okay, if the same compound is missing this plus ozonolysis, the same thing, this will not result in a ketone. It will result in aldehyde. You don't believe me? Go ahead and try adding the double bond O to this carbon containing the double bond. So this would be double bond O. Remember, there's two hydrogens here, right? Which was missing here, which is why we ended up with a ketone and not here. Here you end up with this hydrogen still there. All you got to do is break this, add a double bond O plus, and you add a double bond O here. Now, let me get a different color to box this so you can see the difference. This right here, folks, is not a ketone. This is an aldehyde. I've shown both just to explain my idea clearly. This is a ketone. This is a ketone. Because you cannot have hydrogen on either side of the carbon containing the double bond O, which in this case, one of the places there is. So it cannot be a ketone. Neither of this is a ketone. Both of these are ketones. All right. I got one more, or I think two more reactions on synthesis of ketones, and then we're going to go into applications. All right. So stay tuned.